Okay. I got that the recording was in progress. Okay, perfect. So, first of all, thanks. We would like to say that it was, of course, a great honor to be awarded this prize. And we would like to very warmly thank you for inviting us to give this colloquium talk about some of the related queries. And we would like to thank all members in attendance today. So indeed today with Domènec, what we're going to do is we're going to discuss certain game theoretical problems in spatial ecology. We will try to give a rather descriptive talk of some to give a qualitative flavor of the results we obtained in the paper you just mentioned, as well as some other results related to a work we recently finished with Ziad Kobesi. So, in these papers, the main question that we were actually trying to understand at a qualitative level is, say you have a certain population of fishes, just so that we can fix one interpretation, and say that you have a population of fishermen harvesting from this population. Is there a way to quantify the influence of such harvesting or fishing on the underlying population dynamics? Now, of course, this is way too difficult a question in general. So what we decided to attack was a limited set of questions which already provided rich behavior. So among these questions, the first one is, let's assume that you are the fisherman and that you are trying to fish as best as possible. Question is then something like an optimization problem. How should a fisherman fish in order to optimize his or her fishing output? The second thing is, now try to take a step back and assume that you also want to get a finer description of the influence of such fishing on the population. And the question is, what are the consequences of the competition between fishermen on the fish's population? And so here what we'd like to understand is you have a bunch of fishermen all competing to get the best possible output. What does this competition lead to in terms from the point of view of the population? And the final question is, well, let's assume, because this is after all reasonable, that this type of competition has nefarious effects on the fish's population. Could we understand how to remedy some of these consequences, of these catastrophic consequences in some settings through coordination of the fishermen? So why this type of problem? Because there was a shift in paradigm, of course, over the past 150 years, say. So, for instance, like a century and a half ago, at the inaugural address of an exhibition in London, Huxley, for instance, said that, well, no matter how we fish, no matter how much we fish, the size of the fisheries and the size of the oceanic ecosystem is such that, well, this is barely going to have any consequence. So the influence of fishing is somehow immaterial on the population. As for a point of view that was somehow convincing and very convenient, because it meant that we didn't really have to worry about what we were doing. But now today, well, we all receive on a daily basis news about the catastrophic decline of oceanic diversity, triggered by a variety of factors, some global scale factors, and some, well, directly related to how we directly treat fishes, and in particular, overfishing. Meaning that people get greedier and greedier, they fish more and more, and at some point, this is just too much, and this is taking too much of a toll on the fish's population. So we have some examples of fish's population drastically declining as a consequence, as a result of overfishing. So this is, of course, related to a very well-known concept in economics, which is at the heart of the two contributions we'd like to discuss today. And this is the tragedy of the commons. So essentially, the tragedy of the commons is the economic concept that encompasses the situation we were describing before. That is, when you have one common pool of resources and a population and a group of fishermen or of people acting by tapping into this pool of resources, their independent, uncoordinated, selfish actions will lead to an eventual depletion of the resources. So two main names in here are Lloyd and Harding. So what we wanted to discuss, because here at this point this was still very general, what we want to discuss are very simple, very basic paradigmatic models on which we can actually do some mathematical analysis. So here the goal is to obtain a qualitative understanding of fishing phenomena and of overfishing phenomena. To attack this, we decided to settle on two types of settings. So the first one will be, we'll be considering a very simple domain with a finite number of players. And here, on this basic model, in a static situation, so no time evolution, everything is at equilibrium, we will be investigating standard economical concepts like the existence of Nash equilibria, the geometric properties of fishermen, so for instance, to understand where should fishermen be fishing, and this will offer us also a framework to discuss the first instance of the tragedy of the commons. In the second part of the talk, we will be talking about the more recent contributions where we will adopt not a bounded domain simple equation setting, but where we will adopt a traveling front point of view. The reason we chose these two approaches is that these are two very standard approaches in mathematical biology. And in the case of a traveling waves approach, what we will see is a very dramatic instance of the tragedy of the common, as well as an example of how coordination of fishermen can actually lead to better results for everyone. So, of course, as a disclaimer, because I know, and we were told that many people here probably have better background than we do in biological and ecological applications, our goal here is really to study simple mathematical models with, of course, a limited range of applicability, but that are known and used because they can capture in an accurate way qualitative behaviors. So, in general, the model will be merely a reaction diffusion equation. So here in this equation, the unknown U is going to be the fish's population density. And this population is subject to three types of influences. The first type of influence is a random diffusion. So your fishes are going to diffuse inside your domain. Then there is a nonlinear term, so plus f of u, and f is a nonlinearity that captures intrinsic reaction to the species. So death terms, birth terms, competition among members of the same group. And finally, but this is all like the fishes among themselves. And finally, we will have a term to model the action of the fishermen. So this is just minus m times u. And U here is a population density of fishes, M is going to be the density of fishermen, say. So here what this term tells you is that, well, when you have one fisherman meeting one fish, he's going to harvest it. Okay. So in the first part of this talk, I will discuss bounded domain finite number of players, and Domènec will take the second one on traveling waves. So in that first part, I will be discussing the paper that got awarded the Karl-Peter Hadler Prize, and let's start writing. So the setting is the following one. As I said, we're taking a very simple model. So here we take a very simple reaction term, and we take it of monostable type. So f of u is equal to u times 1 minus u. So you have some form of linear growth of the population plus a saturation effect taken into account by a Malthusian death term. So if you have too many people, there are too many people for the environment to be able to support them. So they start dying. So we assume that the fishes live in an inescapable domain. So that would mean at the PD level, we're working with Neumann boundary conditions, but morally it's just that, okay, they cannot leave the domain. And we also assume, as I was saying here with a finite number of players, let's assume for the time being that we just have two players. Now, the two players, maybe I will refer to them as fishing companies. So a fishing company, what does it do? Well, a fishing company has to devise a strategy of fishing, which is going to be you have a domain, and the fishing company decides how much it fishes in one spot and what this spot looks like. So this corresponds to a spatial strategy, which we just say that's just going to be a function of the domain. So here, alpha I of x, if alpha I is equal to 0, you're not fishing. If alpha I is equal to 10, you're fishing a lot. And we're interested in static situations. So overall, if we just put all these building blocks together, what we get is the following reaction diffusion equation. So I assume my population has reached an equilibrium. I have minus mu Laplacian u, so my fish is going around in the domain, is equal to my reaction term minus the influence of the two fishing companies. Okay. So here I just said that the first company is in red, the second company is in blue. The companies, what they want to do is to say, I want to get to devise a strategy to ensure that I am maximizing the amount of fish that I am getting. So we just need to define the harvested fish functional, which is just for the first company, so J1 of alpha 1. So alpha 1 is going to be the strategy of the first company. That's just, well, the integral of alpha 1 times u, so the strategy times the population density. Now, of course, when you're playing alpha 1, when you're the first fishing company and you choose a strategy, this has an impact on the population overall. And so the second fishing company has to adapt to that. So the goal here is to say, let's assume that each player has a limited fishing ability. So we just say that at any given point, you have a maximal amount that you can fish, and that overall, you have a finite number, say, of fishing boats to dispatch somewhere. The question in this context is there a Nash equilibrium? If so, what does it look like? And what happens if the fishermen coordinate? So, just so that we're clear on the notion, what's a Nash equilibria? In the context of a two-players game, so you have your two fishing companies. In a game theoretical setting, a good concept of a solution to a game theoretical problem is that of Nash equilibria, which just means the first player has a strategy alpha 1 star, the second one has a strategy alpha 2 star, and there is no way for either of them to increase their payoff by changing just their strategy and the other one not changing his or her strategy. So you're in some form of equilibrium of terror. Like if you move and the other one does not, you lose. This is a central concept in economics, well, since the papers of Nash, but in general, Nash equilibria do not exist. So a typical example of that is the rock, paper, scissors game, where if you have two players playing this game, they can never reach an equilibrium situation. So this is really a particular feature of certain game theoretical problems. So in terms of our main results, here I will just describe first and hope that my computer does not crash when I'm trying to show you a video. But if the companies are not allowed to fish a lot, we can prove rigorously that there exists Nash equilibria. And geometrically, the situation is a bit complicated. What we wanted to understand, Domènec and I, was, is it true that fishing companies should fish in the same spots or should fish in completely different spots? Well, surprisingly, this will very strongly depend on the different parameters of the problem. It depends on how much they're allowed to fish. It depends on the maximal amount of fishing that they're allowed to have at one given point. So this is a bit complicated. And finally, and this was also surprising, but in line with some of our previous works. Here, if I just come back to my equation, I have a parameter mu in front of the diffusion term. So mu just tells you how fast the population is going. So mu large means very fast, mu small means very slow. Okay, now the thing is that depending on the diffusivity mu, the situation can be a bit different. If you have large diffusivities, so the fishes move quickly and you're a fisherman, it's better to fish always in one big spot. So you're a fishing company, you're sending everyone to the same spot. Now, if the diffusivity is very small, numerically, this is still not completely proved, but numerically, you see that it is better to fish a bit everywhere. And so a bit surprising. And wait, okay, where is it? Yes. So here, of course, this crashes. So I'm just going to show you, I want to share afresh this. Can you now see the slide of fragmentation of Nash equilibria?
Yeah, we can be seen.
Okay, so Domènec can see it, so that's good news. So the thing is that here, we're in situations, we are in situations where the two companies, because of the parameters we chose, have to fish in the very same spot. That same spot is going to be the red spot on my numerical simulation that I'm showing right now. And the only thing we're doing here is just lowering the diffusivity. So here we start with large diffusivity, smaller, smaller. And you see that progressively, even though they are fishing, even though they have the same fishing ability, the speed of diffusion of movement of the fishes has a strong influence on the geometry of the Nash equilibria. Okay, so I am just going to go back to.
Perfect.
So thanks a lot. As I said, some of my PDF readers do not support these videos. As you can see, this is a video not moving. So here, that was a bit the thing. And now, the other thing that we wanted to show on these two mysterious graphs is an instance of the tragedy of commons. So here, let's forget about the fact that we're just considering two fishing companies. Let's say that what we want to investigate is the case where you have many fishermen. So the number of players, of fishing companies, is on the x-axis. So here you have it between 0 and 10, over there between 0 and 200. And in the sharp color, so the dark blue dots and the dark blue red, what you get is the following information. You get in red the total, so we're simulated Nash equilibria, and the red dots, the big red dots, represent the total amount of fishes that is harvested if each fishing company is playing this equilibrium strategy. And in the blue dots, we see an evolution of, the total population size, so the population of fishes. So what we see is that the total population, if people are competing and playing along Nash equilibria, the total population size of fishes is actually going to 0, and the total amount of harvested fish is also going to 0. If you want, in this scenario, if you have 10 players, they will each get 1/100 percentage of the fishes population. In the paler colors, so in the pale red and in the pale blue, we see what would happen if the fishermen actually decided to come together, play one common strategy, and then split the fish afterwards. So here in red, we see that no matter the number of players, if they played a coordinated strategy, the total amount of fishes that they would be fishing would be higher. So here it's constant at 0.25, something like that. But also, and this is what kickstarted our next contribution, the total population of fishes actually survives. So here you see that the total population of fishes is stabilized at 0.5. So if they coordinated, people would harvest more fish. You could see during the computation that each individual fisherman would make more, and the population of fishes would survive. So this was an example where essentially, we took advantage of the very specific structure of our problem. We did some explicit computations, and we have this first instance of the tragedy of the commons. Competition leads to everyone is losing, including the fishes, while coordination in that setting, everyone is winning more and the fishes are surviving. So that will be it for my part of the talk. And now I will leave the floor to Domènec, who will now tell you about the things that we did with Ziad.
So as Idriss well explained, so thinking on this example in which we plotted a sequence of Nash equilibria with depending on the number of players, and we see how the population of fish is declining as well as the amount of harvested fish. We're thinking on having a model that also has already infinite number of players. So the differences between this work and the other would be, first of all, that we will take more a microscopic view on the problem. So before Idriss was speaking about companies and thinking where the company should fish and deploying a strategy that would depend on areas where to fish. And here we would rather think on individual fishermen that fish in a certain point and move. And also we'll also take a dynamical approach. So first of all, I don't know why I cannot change. Oh, here. Okay. So I'm gonna explain a bit of the population model. So here we will be working on bistable equations. So we'll have a reaction diffusion equation where here theta is the population, and we'll have a nonlinearity f, which is bistable, which is this picture here at the right. I think this is covering you. Wait, do you see the? Oh, no, okay. So why is it called bistable? So if we were to look at the OD level, so taking out the diffusion, so we would see that if your initial data starts below this critical threshold eta, so your population, the field is negative and your population dies out naturally. This is also called in mathematical biology or in biology the Early effect. So the density of population is too low, so the population they don't have the probability of finding a mate might be quite small, so the birth rates drop and the population naturally dies. However, if you start in an initial data which is above this this critical threshold eta, your population grows and goes to 1. So these 0 and 1 are stable points, and that's why this nonlinearity f is called bistable. So, and this LA effect is something that the nonlinearity we treated in the previous paper that doesn't show. So it was a monostable equation with a positive there's a positive derivative at the origin, so it was not showing this kind of property. So another very feature that that we are interested in are that these models, like also the monostable models in dynamical setting, show the traveling waves. Traveling waves are special solutions to the reaction diffusion equations that can be written in the following form. So you can have a profile that here we wrote theta, capital theta. So and is basically translations of this profile. So this has been studied for many years, since the 30s, from the articles of Fisher, Kolmogorov, Petrovsky, Pleskanov, and also in the 70s. So here, what is relevant for us is that if you fix a point, let's say 5, you see that the population of fish, denoted in blue, is invading. So if you don't, the population naturally is invading. Also, these solutions in generic conditions, they enjoy dynamical attractivity. So, and now I'm moving to the what we'll call the fishing problem. So we'll consider a solution of this reaction diffusion equation, and we'll have the assumption as more on the lines of Huxley, but an individual fisherman doesn't have the individual influence of an individual fisherman is negligible. So that one individual alone cannot the amount that they can fish is negligible. So, and what this fisherman would do. So we'll think here we have a boat, so which is this point here, and you would fish what you see there. So that's why here in that term here, we have the evaluation of theta at the point f of t. X of t is the position of the boat. So you would be interested on being in positions where there are fish. So if the fishes were concentrated in that boat here, you would like to move your boat and be in the regions where there are a lot of fish. However, to move the boat, it will cost it will cost you something. It will cost you some petrol. So we would put here also a control cost. Control cost in the sense that you will have to spend this to move. And so the position would be denoted by this ODE, and we also will add a discount factor. This is typical in economics, and we're basically saying that you prefer early rewards than later rewards. So, but we as we said, we're going to consider an infinite number of players. So first, we assume that every player has a negligible impact, but we are going to consider infinitely many of them, and then these all players, they have an impact. So here I denoted like by M of X and T the density of all fishermen, and this is also subtracted in the same manner that in the previous model, from the total number of fish. So you can think here, like in the initial, for example, initial density might be this one I denote here, and now each player, each individual fisherman, each macroscopic fisherman, it's going to play selfishly. So, and you would model this evolution of this M by a continuity equation. So like when these fishermen all move, they will change, the distribution of M will change, and also it will have a different impact on the population. But as I have introduced before, like not every type of this is not going to be for any type of vector field alpha. It will be for the alphas that are basically optimal. So basically what we are saying here is that at every individual fisherman is playing optimally, and we are looking at how the density of fishermen is evolving, and this is also impacting on the population. So this is a context of mean field gains. So that and so here I have not written the full system, but you could derive Hamilton-Jacobi equation that would model the optimal policy taken. So, and what are we interested in? So here, after having this microscopic model, we would like to understand how the properties of this game, but more precisely going on the lines of what we were saying in the previous in the previous talk. We would like to see how can fishermen extinguish the population. So more specifically, so we would be in situations in which the fishermen, if there were no fishermen, the population invades. As the picture I said I showed before, if there are no fishermen, the fishes invade and all the sea. And now we are thinking, like, is there a way in which the fishermen can extinguish the population? Of course, extinction can be done in many ways, but we will center ourselves in traveling wave solutions. So we would be looking for a traveling wave that has the reverse sense. So if before the fishes were invading, we would like to look for traveling waves in which the fishes get extinguished by the fishermen. Up to this point here, we would say, like, just this question: could you extinguish this population by some action of the fishermen? And the answer is yes. However, up to this point here, we are not saying anything about how if this is optimal or not from the perspective of the fishermen. So, and this is actually the result we have. So basically, what we can see is that there are reverse traveling waves. So like the one I'm depicting here in blue, you see the population of fish. In red, you see the density of fishermen, and that they are along moving. And if you fix any point, for instance, you fix the point 30, you see that how at the beginning you start with a population of 1, and after some point it gets extinguished. So for fixing a point X, So if there were no fishermen, the population asymptotically would be 1. But if you consider this consider selfish fishermen, when fixing this point x, when t goes to infinity, the population at this will be 0. So, and this is optimal for every player, given that the density of fishermen is moving as I show here. An individual fisherman cannot improve their strategy rather than to follow at the same speed than this density. So in this sense, this is also a Nash equilibrium. So, but actually, one of the main questions one could ask for now is that, okay, you told me about that if there are no fishermen, the fishes get spread in the whole domain. But now you consider fishermen, the fishes get extinguished by the selfish action. But what if there were no selfish? Like, could maybe like the when I'm considering an optimization problem, or there is no way to do better than to extinguish. And this is also another result we have, that if we consider the total payoff of all the individuals, which means if I consider like all the fish harvested for every player, and I consider all the control costs of every player together, and now you can find strategies in which, like, basically what you're saying here is like, instead of every boat being selfish, I'm gonna say I'm gonna say to each boat how it has to move. So they are not allowed to choose. So I'm just they are coordinated. So. And the distinction doesn't happen. I can just say a strategy in which they move in a way I say, and there is no extinction. But moreover, there is each individual fisherman will fish more than if they were competing and there was the Nash equilibria that I was portraying before. So it's kind of a prisoner's dilemma situation in which you have if you are competing, so you work to get 2 choices. Like this is you can either compete or you could even collaborate and get more. So kind of a conclusion here. So first of all, a key part of this study from the biological perspective is that the reversal of extinction is a combination of these 2 effects. Like this is, we strongly use that there are the nonlinearity can show the Lee effect, and we put also a harvesting game. We also modeled, like in we have a mean field formulation. There were infinitely many fishermen, each one with negligible impact, and they were acting selfishly. And we observed the tragedy of the commons. So extinction does not necessarily happen if the fishermen collaborate. These are saying necessarily because we have this result for certain regimes, not for any regime. And this is all. Thank you for your attention. So this is Ziad Kobeisi, who also worked with us in this last paper. He is a researcher in INRIA, and he's also an expert in milking games. Thank you very much. And if there are any questions, I would be happy to respond.